We've been talking about our good friends Oracle going back and forth out here. They're still going, but they brought in some support boats. So we're gonna have to up our game a little bit. So to break, don't eat your cookie. We're gonna get out there and we're gonna get them. Somebody noticed on Twitter that they brought a single point of failure. So it's their big sale, one sale. So we're gonna go out there and we're gonna take the sale. This is gonna hit the news, isn't it? A bunch of open source hippies take over Oracle. Okay, so our next talk is, this is one that I've been looking forward to. Last year at our summit, we had a talk by Matthias, and it was about Titan, and it was a graph database. What are we talking about a graph database for? Well, it's really interesting how well these two technologies work together and how Titan uses Cassandra, but that was one of the most viewed videos from that conference, and it really hit a lot of people, I think, in their use case where they wanted it. Now I see there's a lot of people filtering in here because this is a very good topic. But without any further ado, I'm going to ruin your last name. Matthias. All right, I'm going to say Broecheler. You don't have an umlaut, I'm sorry. All right.
Cool.
That's close.
All right, thanks a lot. Hello, everybody. It's great to be back at the Cassandra Summit to give you an update on what we've been up to with Titan and what we've accomplished in the last 10 months, I think it is. We presented last year in August, and yeah, now we're back here. The bulk of the presentation today, we're going to present a use case with Pearson Education on educating the planet and how they have been using Titan to scale online learning. And while I'm doing that, I'll also try to slip in some of the technical details of how Titan uses Cassandra efficiently. Titan is an open source distributed graph database built on top of Apache Cassandra. Yeah, we're actively developing it and have been doing so for pretty much exactly 1 year. And I think that's a good point to say thank you to the community that is built around Titan. Without that community, it wouldn't have been possible to accomplish what we have in pretty much exactly 12 months from the day after tomorrow. June 14th, we released Titan. June 14th of 2012, that was the alpha release. That was the first prototype of Titan that we put out there. We put it up on Hacker News, and it somehow bubbled up to the top, and we were like, wow, there seem to be people actually interested in this. And so we went to work on the 0.1 release that came out a good 3 months later. And ever since then have been cranking on performance, trying to make Titan better, getting more features in, features that were requested. With the 0.2 release, we did a big push on performance. And then just about 2-3 months now, we put out the 0.3 release, which was a major rewrite of Titan. We basically refactored the entire internal core of Titan and made it a lot better, a lot stronger. We put in indexing, so now you can hook up Titan with Elasticsearch. You get full text search, you get numeric search, you get geo-indexing, and so on and so forth. So with that, yeah, a lot of new stuff came to life. And Titan also got a brother with Faunus, which is the analytics side of Titan. So Faunus is a Hadoop-based batch analytics graph framework that works nicely with Titan, and I'll get back to Faunus at the end of the presentation. But before we dive into all of that, Titan is a graph database. How many people know what a graph database is? Just by show of hands. All right, good. I think that's definitely a majority. And typically, this is the point where I would launch into like a monologue explaining what a graph database is and giving you a million reasons for checking out a graph database. But at a recent conference, somebody came up to me after the talk and said, look, I really, really like graph databases, but if I have to listen to you explaining graph databases again, I'm going to switch back to relational systems. So I don't want to induce that kind of pain, so I'm going to keep it really, really, really short this time and just say this. Graph databases are vertices connected by edges. Edges have labels, and both of those have properties that describe them further. As in this example, we have people here, Hercules and a monster, Cerberus, represented as vertices. We have one edge between them, a battled edge, that has a time point of 12. And that's pretty much all you need to know in terms of terminology and how you would go about dealing with a graph database. So that boils it down to exactly 30 seconds. One question, however, that we haven't been able to give a good answer to is when should you use a graph database, or when should you consider using a graph database? And typically, there are a bunch of use cases I can rattle off and a bunch of reasons for why you may or may not want to consider a graph database. But I think we can concisely boil it down to this. If you look at your application, ask yourself the question of how much value is in the relationships in your domain. Or rather, how much value do you want to get out of the relationships in your domain? If that value is very low or none, you probably should be using a key value store, right? That's the simplest data model there is. Just a key maps onto a value, super simple to use. If there's slightly more, you get into the big table, the document data model, where you can have key internal structure. So either document structure, or you have the wide rows that you have in Cassandra or other big table type implementations. If you need more structure, more relationships than that, you can go with the relational data model, where relationships were sort of bolted on with the concept of foreign keys. But if you want to go full in on relationships and get every bit of value out of those, you're probably best suited with a graph database, because graph databases are built for relationship analysis, meaning their internals are highly optimized for graph traversals, relationship traversal, but also the interfaces, the query language, everything around graph databases is optimized for analyzing relationships. So if you want to get all the value out of relationships, a graph database is a good way to go. And this is purely looking at it from a domain perspective, right? We haven't talked about scaling. We haven't talked about any of these aspects, which I'll get to in my talk. This is just to give you an idea for when should you bring graph databases into the conversation. So graph databases are for getting most out of your relationships, and that is what motivated Pearson Education to look into graph databases for a new online learning platform that they're developing. A lot of people probably know Pearson Education from textbooks. They're a big publisher of textbooks that are used in schools and universities all over the world. Some of you may know that they're also doing a lot of work in virtual learning platforms. For instance, they have a product out called OpenClass, which allows students to register for courses, join discussions, look at course content, and so on and so forth. And now they're developing a new platform that is looking at an entirely new world of education. We have seen some really interesting developments in education in the last couple of months to years, and that is the rise of those massive online classes, so-called MOOCs, where you have one teacher and thousands, if not hundreds of thousands of students in those classes. One of the popular ones was Peter Norvig and Sebastian Thun at Stanford gave a class on artificial intelligence, and I think they had well over 100,000 students in that class. So now with that concept, it is possible to develop, to bring world-class education to rural cities all over the world. But one interesting challenge with that is how do you get the social component into learning, right? One part is delivering the content, another part is to get the social back into it. So Pearson Education is looking at a way to bring the content delivery together with the learning experience that is inherently social into one learning platform, a virtual learning platform that marries concepts both from massive online learning classes with social networks. And quite naturally, they were thinking about graph databases to drive that kind of development effort, because they're thinking, well, if we want to make that a success, we need to figure out how we can deliver data-driven services to make such learning environments effective for the student and also manageable for the teacher. Because if you imagine you're a teacher with 100,000 students, that's a hell of a lot of work for you to do. So you need to have some sort of support built into the platform. Let's look at what their platform looks like to see what motivated them to look into graph databases and Titan in particular. So this is a very simplified version of the schema that they're looking at. You will see familiar concepts like people, institutions, courses that people are enrolled in, that teachers teach. You'll see discussions, which are the discussion forums. Discussions can have comments on them, and comments have comments on comments. There's the concept of a share, which is something that is borrowed from the social network domain, similarly to how Twitter works. So a student can share any piece of content or anything they would like to share with other students, and then those students that follow them will see that piece of content as well. Right, so we have both elements from online education and social networking married together in this simplified schema here. When they started off developing this platform, they had a bunch of different teams developing these components, and with that, they had a bunch of different storage solutions that entered the picture. Some teams were, using relational systems like SQL Server, which was very popular. Others were using MongoDB. There was Cassandra in the mix, and even some Voldemort was thrown into the picture. Now, while that gave a lot of autonomy to the individual development teams, it made it really, really hard to do anything with the data, to develop interesting services from the data. Because if you wanted to interrelate, for instance, the follow relationships with the discussions that were taking place, well, then you had to run 2 ETLs out of the respective storage backends, trying to then join the data somehow and then develop any kind of platform on top of that. And if you wanted to do that in real time, well, good luck. So now all of that can be stored in Titan. Titan has a very integrative data model. As a graph database, it has a flexible schema, which means it does have a schema. So Titan has a schema. It will enforce a schema. But the schema can be defined at runtime. So you can tell Titan at runtime how to extend the schema and therefore be able to accommodate additional services or additional concepts in your domain. But what makes graph databases really interesting is the kind of services, data-driven services that you can now develop. One of which I'll explain here. It's called Discussion Rank. Discussion Rank is something that came out of a sort of a lab environment inside Pearson, a collaborative adventure where we tried to figure out how can we support teachers in driving discussions for a course. So it's well known that one of the best ways to make students understand new concepts is to have those students engage with one another and explain the concepts to each other. If you have to explain something, you learn it much better. So that's well known. But how do you do that in a virtual environment? So one of the ways you can do that is you can engage students in a discussion. So a teacher can kick off a discussion and then try to motivate those students to engage in a discussion and interact with one another. Now that works very well at a small scale, but when you have a class with 100,000 students, again, that becomes very, very tedious because you might have hundreds, if not thousands, of discussions happening at the same time. Now, a teacher cannot possibly look at all of those discussions at the same time, so what do? The idea behind Discussion Rank is to rank discussions based on their fruitfulness or how likely it is that those discussions are on track and therefore don't require any further teacher intervention. Whereas other discussions might be derailed and therefore the teacher should step in, look at those discussions, and probably get it back on target. What we did to accomplish that is we looked at multiple factors, and this is where graph databases are really great to integrate those all into one picture. If you look at the discussions and if you look at the discussion tree that is being spawned from a starting discussion topic, you can see that you get a tree structure for each individual discussion, right? There's a starting topic, let's say, was Shakespeare one of the greatest poets in England, let's say, as an individual starting point. And then you have students argue pro and con on that particular question. So you get a tree structure out of that. And you can look at the structure of that tree. So is it a very bushy tree, so a tree that has a high branching factor? Is it a very thin, narrow tree? So it's essentially just one individual branch. And that structure of the tree gives you some indication of how wealthy or how healthy that discussion is. Another thing you can look at is who is engaging in the discussion. Are those just students who know each other already, so students who follow each other, or are there interactions between students who have not previously interacted? So we can pull in the fellowships relationships. Another thing we can do is we can try to understand, is the discussion on topic? We can look at the concepts that are being mentioned in the individual discussion posts and relate those to a concept map that we have extracted from Wikipedia. There's a project called DBpedia, which tries to codify the human knowledge captured in Wikipedia as a graph. So we can look at the concepts and how they're related to another. For instance, the fact that PageRank is related to eigenvector centrality, which in turn is related to linear algebra, right? So we have those relationships captured, and then we can look at discussion topics and see whether they are on the topic of the course, which we have also captured in this graph. So you can see we're traversing various relationships from concepts and their relatedness to discussions, their comments, people following each other and people authoring the discussions to understand whether or not a discussion is healthy or whether a discussion needs possible intervention by a teacher. Bottom line being that Titan allows you or gives you the capability to do that kind of relationship analysis very effectively. The query languages and the entire architecture of Titan is geared towards that type of relationship analysis without any kind of joint processing, just merely traversing the graph as quickly as possible. Of course, if you have the mission of educating the planet, one of the very important aspects of choosing any kind of storage solution is, can this scale? And this is obviously one of the very interesting questions of this entire conference is, how do you scale, and can Titan scale to the kinds of requirements that an online platform, online learning platform has if you want to distribute it over the entire planet? Now, when you look at scaling, there are basically two factors that we're considering here. One is, can it scale in the number of transactions? And two, can it scale in the size of the graph? Right, so number of transactions and how many people can concurrently interact with the graph, and the size of the graph is just the sheer amount of data it can hold. To answer this question, we started a benchmark. And basically we said, okay, if we want to educate the planet, let's do a benchmark where we simulate 3.5 billion students, so that's about half of the world's population, being on our learning platform. So hopefully we'll get to that point, but for now we're just simulating it. And we ended up with a graph with 6.2 billion vertices and 121 billion edges connecting those vertices. So this is a massive graph. And in fact, we don't know of any graph data, or any social network graph data of that size that's freely available, so we had to generate it. We used census data to generate names. We used scale-free data generators that we implemented and subsequently open sourced to generate the network structure and make it as realistic as possible. We used MIT OpenCourseWare to generate course titles and the concept in those courses, and so on and so forth, to end up with 3.5 billion students, about 780 million courses, about 180 million teachers at 1 million universities that we generated. First, we had to, so this is about 10 terabytes of data that we ended up with. We put all of that data into S3, and now we had to load it into a, wrong button. We had to load it into a Titan Cassandra cluster. What we did is we used 16 high I/O instances, so those are the new Amazon EC2 instances that have the SSDs in them, the 2 terabyte SSDs, and we put them all in one placement group. One of the things that Titan allows you to do, it allows you to run Cassandra embedded. So you can start a Titan cluster that internally will start Cassandra, and then the interaction between Titan and Cassandra are not over Thrift, are not over SQL. They are direct in JVM calls against Cassandra, thereby removing any kind of overhead, which was important for batch loading the data. Because at 121 billion edges, you need to be really, really fast in ingesting that data. And we actually achieved a data ingestion rate of 1.1 million edges per second, which is possible due to the aforementioned embedding, but also because we have a special batch loading mode in Titan that will remove certain consistency checks in Titan that are due to the data model and the schema design, and simply just load data as quickly as possible into Cassandra. We also did a bunch of optimizations to Cassandra itself, like increasing the size of the mem table for the loading and removing the compaction throttling. So that made it possible to load that data set in about 1.5 days, which is pretty fast considering the size of the data at 121 billion edges. And then we moved on to a transactional workload. So now all the data is in the database, and so now we're simulating a lot of students concurrently interacting with the system. So what we did is we started another 80 M1 medium instances, and they simulated web servers. So imagine the students would be hitting those servers from the web, and then those servers would be asking queries against the Cassandra cluster. We did not simulate the web part because that doesn't have any impact on the database itself, but we simulated all those transactions that would occur against the database. And in fact, we came up with 16 transactional templates, and each instance would take a random user and then take a random transaction template, substitute that user into the template, and execute the transaction. And that's how we simulated a massive scale concurrent access to the graph database. To give you a flavor of what those transactions look like, here's one query that we wrote, which is a follow recommendation. This is written in Gremlin, which is the query language for Titan. And as you can see, what we do here is we define a set X and a map M. And what we want to do is we want to find out good recommendations for a particular user. That user would be randomly sampled, as I mentioned before. So what we do is we traverse out from the user. We look at everybody that user follows. And then we aggregate all those users in our set X to make sure that we don't recommend any of those, because that would obviously be pointless. But then we take one further step out. So we look at who do they follow, and then do a group count on that. So we look at everybody who I follow, who do they follow, and then I aggregate those by counting, counting the duplicates essentially. And then the logic behind this recommendation is, well, if the people I follow these people more frequently, then probably those are good recommendations for me as well. And so that's what we do. Down there we sort, in the third line, we sort those results and return back the top number where number can be specified. So let's say the top 10, and we would return those to the user. So this is a followership recommendation that we implemented. There are other kinds of recommendation algorithms that we implemented, all of which were implemented in Gremlin, which, as I said, is the query language for Titan, and actually not part of Titan itself. It's part of the Tinkerpop ecosystem. And that's an important part of Titan as well, because it constitutes the ecosystem in which Titan is embedded. We have Titan as a native blueprints implementation, which means it benefits from all the components of the Tinkerpop stack. Gremlin being one of those, probably the most important, but there are others, like the Replication Graph server, which allows you to expose any Titan server as a REST endpoint. So it makes it very easy for web development. There is an algorithm package called Faunus, which implements a bunch of standard algorithms. And we're now working on a very new type of algorithmic framework that will be coming out shortly. So a lot of things that you need when you're dealing with graphs are provided in this ecosystem. So Titan itself, being a graph database, is important. But as important is the ecosystem in which Titan is embedded. Going back to the transactions, we ended up executing this transaction benchmark, and we're able to execute about 10,200 transactions per second on average. Now that is obviously lower than the numbers that Jonathan shared with us earlier, but remember that those are not just individual sort of atomic transactions. Those are complex traversals of the graph, like the followership recommendation that I just showed you, which is a multi-step traversal over the entire graph. And in fact, just to give you like a rough idea of what those transactions are, all of those are specified in the blog post. I just gave you sort of an excerpt here. You see that we have transactions here like a student retrieving all of the content for a single course in their content list. So we have multiple pieces of content that are being traversed to. We have adding fellowships. We have student reading their streams. We have students reading the most recent comments for all of their courses, and so on and so forth. And you can see in the column over here, we have the average transaction times for those queries. You can see those vary widely, and also the standard deviation of those varies widely, because the complexity of the individual transactions varies with that. Now, we talked about the benchmark and the fact that we can scale Titan. One of the things I want to get into now just a little bit is how we scale Titan. Like, how does Titan actually work underneath, and how does it use Cassandra to deliver the kinds of scale that we were talking about? There are three things I want to talk about. The first being vertex representation. So the way we represent the graph is that we store each vertex as a row in Cassandra. So here we give an example of an example vertex for Hercules. That vertex is assigned ID 5, and so we have a row in Cassandra with that ID 5, and then we have one column for each property associated with that vertex, and one column for each edge associated with that vertex. So essentially, we're storing the adjacency list of each vertex with the vertex. One of the important aspects here is that there is an induced order on the edges, and in fact, Titan allows you to define what that order should be by defining primary keys for a particular edge label. So for instance, here we have defined a primary key as time on the battled edge, meaning we want battle edges to be sorted by time. What that allows us to do is allows us to efficiently query for all of the recent battles that Hercules engaged in, or for all battles that fall in a certain interval. right? And that makes coring very effective, in particular when you have supernodes, so vertices with larger edges incident upon them. And what this translates into are row index retrievals in Cassandra. So we use the row indexing mechanism that comes with Cassandra to execute those queries efficiently. Now, with the adjacency list representation, one of the downsides is that we're effectively storing each edge twice, right? One on the incoming and one on the outgoing vertex. In order to mitigate that duplication in storage, we invested a lot of effort into making sure that we can represent edges compactly. So we use variable long encoding for all of these IDs that we have. We look at the ID delta for the vertex IDs, because typically they are assigned IDs that are in proximity, and thereby we reduce the footprint of the ID, of the stored ID by using a long encoding scheme. Plus, we allow the user to define the primary key and a signature key for a particular edge label, and that in turn will make Titan use compression schemes when storing the respective properties on the edges. So the bottom line here is we use various techniques from variable long encoding to delta long encoding to object compression to metadata removal in order to be able to reduce the footprint for each individual edge as much as we possibly can, and thereby reduce the storage footprint. Lastly, one important aspect of Titan is graph partitioning. And that's one of the things that we're spending a lot of time thinking about and trying out various approaches. It's a very challenging problem. As we all know, it's actually NP complete. And we're looking into how we can effectively partition graphs. The way we do that in Cassandra is we essentially map the partitioning strategy onto the ID scheme and thereby onto the tokens that get assigned to a particular vertex. We use byte order partitioning in Cassandra, so we have control over where a particular ID, or token for that matter, gets assigned. So we know what machine a particular vertex gets assigned to. And so what we can do, as illustrated in this example, if we know a good partition cut for a graph, we can then assign the IDs such that we know that vertices which should be close together are actually allocated to the same physical machine, or in fact to the same V node, by which factor they will then be on the same physical machine. One of the key questions, of course, then is, well, how do you decide whether or not two vertices should be on the same machine? And that, in fact, is a very challenging problem. For the Pearson study, we used a transactional bound partition mechanism. So we said that vertices that are assigned in the same transaction, we essentially just do partitioning on those vertices, which works pretty well because a lot of the relationships are centered around universities and the students contained in those. But other use cases might have other partitioning schemes that are more effective. Titan allows you to plug and play your partitioning mechanism into the database itself, so you can optimize the partitioning strategy for your particular use case. But most certainly, I think graph partitioning is the one subject in Titan that will keep us busy the longest, because there are lots of very interesting questions that we have yet to understand and find appropriate solutions for. Now, we talked about Titan a lot, which is a real-time graph database. As I mentioned in the beginning of the talk, there are further components to the Aurelius Graph Cluster, Titan being one of them for the real-time graph database, but there's also Faunus. Faunus is Titan's brother in a way, in that it is a Hadoop-based graph analytics platform. It works by compiling gremlin queries, so that's the query language I was talking about earlier, into MapReduce steps. So you can run MapReduce graph analytics jobs on top of Titan by sucking the data out of Titan, then doing the batch analytics, and then either writing the results back into Titan or into HDFS or some other output format to get the results of your computation. Faunus, in and of itself, it's its whole own beast. So I could give a whole talk about Faunus, but you can also check it out online. Documentation and all is available. This is just to say that Titan is one component. Faunus is a whole separate world. It enables you to do batch type analytics, so you can look at degree distributions, you can look at any kind of statistics on the graph, or you can do very extensive traversals where you have to traverse out of every vertex in the graph. So those are the kinds of things that Faunus allows you to do. And then lastly, currently under development and coming out pretty soon is Fulgora, which is a graph traversal framework which is optimized for in-memory traversals. So if you have very extensive traversals where it is too expensive to go to disk or even just any kind of intermediate representation, then Fagora will make it faster because it resides entirely in memory. The point of this slide is really to give you an idea for how all these pieces fit together, and the fact that we're building one coherent graph framework that allows you to address various graph use cases within the context of just one framework. With that, I want to conclude my talk. I want to thank Pearson for their continued support on this, in particular Steve Hill, who's been driving a lot of this and giving us a tremendous amount of feedback on Titan, and pushing Titan really to become scalable and performant for their use cases. Thanks. Are there any questions?
Hi, I'm just learning graph databases. I'm wondering, how does Titan compare to other graph databases like Giraffe, and there's a new one called Bagel, I think, on top of Shark?
Oh, Bagel?
Yeah.
So particularly when you bring up Giraffe, so Giraffe is actually not so similar to Titan. It's more in the Faunus framework, meaning it's more comparable to Faunus, meaning it's a batch graph analytics framework. So it also allows you to analyze graphs, but it does so by looking at a graph as a static graph, and then you run a batch job over that graph. So you can extract statistics, or you can do any other kind of computation, but the graph is static, and your computation is a batch computation. So with the overhead of Hadoop and so on and so forth, you would expect your results in minutes or hours, depending on the size of the graph. Titan is an OLTP graph database, so the point here is really real time. So you can answer queries, and the results should come back to you in milliseconds, so you can drive web applications or any other kind of user-facing application. Right? So that is the comparison to Giraffe. There are other graph databases, obviously, that are also OLTP, so they are real-time graph databases. To those, I think one of the characteristics of Titan is it's open source, it's Apache 2, and it's one of the first graph databases that is looking at scaling graph data, meaning scaling it across multiple machines. So I think that those are the characteristics that make Titan stand out. Any other questions? I think there's one over there.
So what is this Aurelius? I didn't catch that.
Oh, OK. So yeah, maybe I should have said that. So Aurelius is the company behind Titan and Faunus and the entire Aurelius Graph Cluster. So
is that associated with data stacks?
No, it's an independent company. We're all about graph data. So we're really interested in building tools and services and platforms that allow you to do graph analysis at scale. Okay. And we're using Apache Cassandra, but we're not a sort of subsidiary or anything of DataStax.
Okay, so now coming back to the question on that massive simulation, seems very, very, very impressive, that simulation that you did. So you mentioned, prior to talking about the simulation, you mentioned about this being used for real-time social analytics. So how are you able to simulate? I didn't catch how you were able to simulate the social interactions in that.
How we were simulate. So what we did is, for the benchmark, what we did is we had these 80 instances, and each of these 80 instances would randomly choose one user of the social network, effectively. And then we would pick a transaction template. So we would say something like, this user is reading all of their courses and all of the content associated with their courses. Or this user is looking at all of the people who are part of a course that this user is enrolled in, or things of that nature. So we basically had these templates that are characteristics for an interaction that a user would have with a social network. And then we would substitute the randomly chosen user with that template and then execute that transaction against the graph database. Right? And thereby we would simulate a complex interaction, like a student logging in, clicking on a course, clicking on everybody in that course, or a student logging in, looking at all the content. These types of interactions would be simulated in this way. Right? And then we measure basically how long does it take, how many transactions can we execute per second, and a bunch of statistics around that.
Did you by any chance look at support vector machines for partitioning?
Do we support?
Doing the support vector machine for your partitioning, taking a vector minimization on a hyperplane. That's kind of what you showed.
Oh, OK. So no, the techniques we're looking at for graph partitioning, the ones we found most effective, are label propagation-based mechanisms. And that's sort of the direction we're going in. As I said, however, we decided to make the partitioning mechanism plug and play in Titan because we realized that an optimal partitioning strategy is always dependent on your domain. So if you have any kind of domain knowledge or any kind of favorite algorithm for graph partitioning, we wanted you to be able to plug that in. So if you have such an algorithm or an implementation, you can easily plug that into Titan, and Titan will handle all of the mechanics, so all of the actual assignment of partitions and so on and so forth. But in terms of actual implementations that we have done a transaction-bound implementation of graph partitioning, and we have done label propagation, which are the ones that we found most effective.
How many vertices can you return at one point? Because we have an example where we have 20 vertices that relate to each other and we need to return it back to the user. Do you think that would be kind of a possible or real thing to do, or is that really just a crazy point?
You said 20 vertices or 20?
20,000.
20,000 vertices.
Because essentially you have one student who relates to 5 other students who relate to 10 other students and so on. So you essentially form a graph.
Yep.
When you're returning all the info, you want to return that student along with the connected vertices.
Yeah, so 20,000 students is a lot. I mean, just to materialize that result set, I mean, that's a lot of data that you need to get out of the database. Typically, we find that in the context of a particular algorithm or particular goal that you're trying to achieve, there are certain subsampling strategies that you can use. So for instance, for the follow recommendation that I showed you, one of the things we're doing is we're subsampling by recency. So we're looking at people who you have recently started to follow and not at everybody you have followed. Right? So that allows you to constrain that search space and allow you to rein in on that combinatorial explosion that you often have with graphs. And Titan can do that very effectively because it amounts to the induced order on the edges that are talked about. So you can therefore use the row indices that come with Titan to effectively extract those edges and therefore those neighbors. So in a lot of use cases, you can therefore constrain your sample space or your search space quite significantly and then only return a couple of hundred, or maybe at the order of 1,000 vertices, but not 20,000 or 100,000 vertices, which becomes pretty slow quickly.
What is the replication factor you're using for Cassandra behind?
For the benchmark?
The replication factor for Cassandra, because Cassandra is what is backing up Titan, right?
Yeah. So the replication factor is configurable. In fact, Titan has a configuration option that allows you to configure that replication factor, and a lot of other things that you would typically configure with Cassandra, like what's your write consistency, read consistency levels. Those kinds of things are also exposed at the Titan level because they directly map onto each other. In that sense, you would use the same kind of logic that you use to determine your replication factor for a Cassandra application also with Titan. And in fact, I mean, if you look at the documentation, you'll see that a lot of common configuration options that you have for Cassandra are also exposed at the Titan level, and you configure them all at once.
So this is regarding your batch framework to inject the data into the system. Is that open sourced?
Yes. Yeah, everything I talked about in these slides is open sourced under Apache 2 or BSD.
Thank you.
I have another question, actually. This is more about the Fulgora, is it? So I just recently came across something called Rec4j, which is a recommendation engine on top of Neo4j. Mm-hmm. Are you planning on something similar for Fulgora, like where you take common applications like recommendation engines and so on? And
yeah. So actually, it is my understanding that Rec4j is sort of generalizing their underlying storage infrastructure so that they can interact with any Blueprints implementation, or they have something similar to that where they abstract away the actual database and just have an interface to that. So in that sense, you could run Rec4j in, on something like Titan. But that has not been done yet. We have an algorithm package called Faunus, which essentially has a bunch of these standard algorithmic templates implemented. We don't have anything like a, like a standard recommendation engine yet, because we don't, with the customers that we interact with, we often see that they use these standard algorithms, but the recommendation engine itself is typically tailored to their particular domain or to their particular liking. So we're not aware of anything that is like a, like a one-size-fits-all recommendation engine. So, but we have these kinds of pieces that you can then use to assemble your own recommendation engine. And a lot of that stuff is either already built or being built as part of the Tinkerpop framework.
You talked about partitioning and how easy it is to change the partitioning in your current setup. Because I can see for certain types of problems, you might want to change the way the partitioning works, okay, for the very same application. So you're looking at one type of questioning, you need one kind of partitioning to make that. So is it easy to change the partitioning, or what is your experience?
So right now, the partitioning strategy would be fixed. So once you decide on a partitioning strategy, you would be using that partitioning strategy. I have not yet come across a use case where you would swap it out for another partitioning strategy. There's actually no reason that that wouldn't work, because you incrementally assign vertices, and so if you change the logic behind that assignment, there's nothing in the existing data that would get impacted. But at this point in time, if you use Titan 0.3.1, you wouldn't be able to change the partitioning strategy.
So which version of Blueprints are you supporting?
Titan works with the most recent version of Blueprints. So Titan 0.3.1 is compatible with Blueprints 2.3.0. And in fact, we're trying to sync that up a little better so that the sub-versions match. But essentially, a lot of the stuff that we're doing in Titan is also, to some extent, driving the developments in Blueprints and vice versa. So the two have been tightly following each other in a way. And so Titan has always been up to date with the most recent version of Blueprints. I think that's it. Thank you very much.